Well, we come to chapter O on polarization, and we're going to see some more surprises from the Fresnel equations. Now, this class might go a little bit longer because I want to review for you lots of things from your introductory physics class with calculus. That's the electricity and magnetism part, because they've done in that class the Poynting vector, the energy density in a capacitor and an inductor, and these things are important for light, and I want to be complete. So yes, you might be a little bit longer today, but half of it's review. At least half is review from things you've seen before, and I want you to master these concepts. So I think it's important to take the time to review from the previous class that you took. And we'll also see here invention. We'll look at Edwin Land, who invented the polarizer, and talk a little bit about inventors and how inventors can inspire us just as well as theoretical physicists. Chapter O, polarization. O1, we're going to look at the energy in an electromagnetic wave. Now, this is treated in Introductory Physics 2. I'm going to assume you were sick that day, and we want to do everything. So let's go ahead and do a review. So we have Y, say, let's put X here, and Z, like we did initially in another chapter. Here's your E field. Here's your B field. And we're heading down the Z axis. So we have the electric field, some amplitude, maximum amplitude, because the sign can't go more than 1. And we will have B, go ahead and isolate that. And then B is B naught sine KZ minus omega T J. And we could isolate that. The connecting equation that we arrived at, the ratio C, which is also omega over K, and remember C is 1 over the square root epsilon naught mu naught. We're in vacuum here. Now, to understand the energy, you see, we're going to look at a little region, and try to figure out here what the energy density is going to be. So like, what's the energy in that little region? So that little region has an electric field and has a magnetic field, but what energy is in that little region that's going to, move, like that energy is going to move to the right? And we know there's energy in light. We feel warm when the sun is hitting you. And we like to get a value for that. So this suggests we look at a model where we have 2 plates, because 2 plates can get us an electric field very nicely. If we have plus here and minus here, remember the electric field is going to point so that it tells you where a plus charge would go. So in this case, like this. Now you're going to have weird stuff at the ends So what we will do is we will assume the plate is big, or we'll neglect that in our model, all right? So that would be here, we would have an area. You know, you can imagine the charges all over that top surface. And here we'll have an electric field. And let's go with having plus Q up here and a minus Q down at the bottom. Now we've already done the electric field for the plates. Remember we did the Gauss's law, that if you have the E dot, very, very easy to do it again. And if you have here, say Q over epsilon naught, this Q is some density times the area. And this is going to be EA. E, if you do one plate, if you're doing one plate with just a plus sign, then E points in either direction. So when you do the top, you're going to get an EA. When you do the bottom, you get an EA. There's nothing on the sides, so there'll be two EAs. And then here, you're going to get E is equal to the A's cancel, and you get this famous result, so the charge density over 2 epsilon naught. And since there's two plates, if you have two plates, you're going to then have a doubling. So for the two plates, the E is going to be this double. We can put back, if you want, the Q divided by the area. So we can use either of these. I think we're going to stick with this one for now. So the electric field is Q over the area, epsilon naught. It's an electric field in there. And we know that when we have our potential, the way the potential works is that the force is minus the derivative of the potential. Now here, what we do is we're looking at the electric field is the force per unit charge. And then when you have your V potential, that's per unit charge. So we're looking at this version. And here, if we look at this, you can kind of just see by inspection that the V has to be E times X, because if you did the derivative, minus dV dx, you get minus E, and that means your force, when you put your Q in there, in your general form, you put your Q in there, in your general formula, remember the force is Q, the E vector. So if you put the Q in there, you get this, and does that make sense? Well, yes, if you have a plus charge, test charge, it's gonna go down. Now, you gotta be careful here. Maybe I put a little T here for test charge, because this Q is not the same as the other Q. This is the charge you're gonna put in the middle of this test to see what happens. But we wanna use this form here. That's gonna be important to use. And if you have the distance here being D, then between the two plates, then this can become D. So you have then a potential between the plates. It's kind of like an MGH kind of thing, that if you take your total height, then you're going to have GZ becomes some MGH, where the Z can vary, but then the H is like where you have it, like where you have the ball before you drop it. So we have this nice formula here. V is ED. And then what we would like to do, we like to find the work done to build this up, to find the energy in the field. So what we do is we say, if we wanted to take a DQ, a charge, and put a plus up here, Like we want to get more up there. Like say you have some battery you're connected to and like you're forcing, you know, a plus charge on here. If you had some like battery like this and you're putting the charge on there, it's going to take some energy to do that. So we want to find out the energy to build up this, to build up that E field that's going to be inside here. So the bit of energy, you know, work that we're going to be like doing on this thing is if you have the potential and you have dq, this is how you set this up. It's like a potential energy problem. So this is the potential energy that goes with this. So the potential per mass like would be this part here, and it's kind of like saying we're going to put more mass, you know, higher up. So what you would do is you would set up, now this would be a very simple case if you have the G and, well, this probably be, maybe just make it H for like MGH. And then if you had a DM, you're gonna then integrate to find out, like, you know, you're taking all these masses and like, you're putting all these stones or all these masses, you're like picking them up to, you know, a height H. The only problem with this thing is that when you put the charge up there, you're actually changing the difficulty. While with the stone, each one's going to be the same difficulty. This is a constant. So, easy problem. But see here, when you have the potential and the little piece of, you know, charge that you want to move to the other place, you're going to change potential. Here you don't change it. So this is an easy integral. This is MGH. But here I got to be careful. So for the V, what we're going to do is we're going to use this formula here. So let's look at this. This is E times D, and the E is up here. The E is Q over A epsilon naught. If I put the D there, this is showing me what I need to put up in this integral. See that Q, that Q is not going to be constant, so that's where we're going to have a little tricky part. So then we're going to integrate from 0 to, say, big Q. And we didn't put all these things in here, the Q, the D, the A, epsilon naught, and dq. And a lot of constants come out. The distance between the plates, the area of the plate, the permittivity of free space. We go from 0 to big Q, and now we have the Q dq. So this is going to be Q squared over 2, and we go from 0 to big Q, so that's going to be D over A epsilon naught, and big Q squared over 2. So that's the energy that we have used to build up this electric field in between the two plates, which is going to be useful when you're looking at the electromagnetic field in a region. So I like to get this in terms of the electric field. So what we're going to do here is we're going to go back to this formula and say now we're at full strength. So if we're at full strength, we have big Q over A epsilon naught. So that means here that the big Q is E A epsilon naught, and that goes in here. So when we do that, we'll have the dA epsilon naught, we'll have the 1/2 floating around, and then we square this thing, E squared, A squared, epsilon naught squared. So when we do that and simplify here, we're going to get the D survives. Here, we're going to have one of the A's going to cancel. And here, one of the epsilon naughts is going to do that. So maybe we take our time on this. We have the 1/2. Let's just worry about the A and the epsilon naught. So that's going to be here, knock this A down 1 power and this down 1 power. And then we can write down 1/2 A D epsilon naught E squared. And when you look at this, you have, see, this is the volume. This is a volume, the volume between the plates, and we wanted the density. So that means this is going to be the energy of the electric field per unit volume. I divide by the volume, I get then 1/2 epsilon naught, and this E squared, I'm going to use the E naught because that's applying that to our electromagnetic wave, where the electric field here is the maximum is given by this E naught. So that is what I'm going to use in this formula, and this is going to be it here. All right, that's like the strength of my field. So that's the result. This is a nice review of introductory physics, electricity and magnetism part of the course. And they also did there the case for the magnetic field, and I don't want to deal with that because that's a lot of effort, and we're taking too much time if we do that for the review on the class. So we're up against a wall here. Notice I did not use the word capacitor here. When they do this in the electricity and magnetism class, they talk about capacitors. Didn't mention that at all. This is tailored for our course. And here they go with the energy magnetic field in a coil, in an inductor. And if you think this is a little bit tricky, you remember inductors are even more tricky. So what do? I need to derive everything, and I don't have time to do this. So we're going to go to a trick I learned in actually introductory chemistry. It was very, very big on this, dimensional analysis. I did have a physics course in high school where I first learned the term, and chemists are good at canceling things out and setting things up. So I'm figuring, since the energy density for the electric field is given by this, and the fields look the same in terms of the sine function, and there's a connecting equation here, of course, but I'm thinking here the magnetic one is going to probably have, say, this 1/2, and it'll probably have some mu naught in there, and it'll then have a B naught squared. So what is the dimension of this energy density? Well, that's going to be energy joules per cubic meter. This means dimensions. Joules, I remember, is force times distance. That's work. That's the easiest way for me to break it down. That's Newton meter. Newton meter is your joules. And then if you divide by the cubic meter, then you're going to get, this is what you need. That's what I want. I want Newton per meter squared. So let's start by finding what the dimensions for B is. Now, Tesla and all that can get complicated, but if I remember that the force is Q V cross B, then B has to be the dimensions of force divided by the dimension of charge and the dimension of velocity. Because, see, if you take the charge and the velocity and you divide the units, you got to get the B. So this is going to be up here, Newton, and the charge is going to be Coulomb, and the velocity is going to be meters per second. So this becomes Newton over a meter, and a second over a Coulomb, just rearranging things, because C and M are at the bottom, and then these two are at the top. So if I go for B squared, I'm going to have Newton squared, meter squared down there, second squared, and Coulomb squared. But what I want is Newton per meter squared, and let's look at the junk that I want to get rid of. If I have Newton per meter squared, I have a Newton hanging around. I have a second squared, and I have a Coulomb squared. This is a good assignment to do dimensional analysis. Could do it now and then. So this is the junk. I don't want that. So now I go on to find what the dimension would be for the mu naught, and I get that from B dot dl. I know that you get a current in a wire, you get this. Now, I don't care about the full Maxwell equation because I just want to play with dimensions. So that means this mu has to be dimensions of B and the dimensions of this length. All right, this length is like a distance, so an R, say, for like distance, and you're going to divide by current. So that would mean that the B, since I already know what that is, that's up here. I already got that one, so I'm going to copy that one down again. Newton per meter second over Coulomb. That's this one. That's what the B is. And then the R is a meter, and the current is Coulomb per second. And if I look at this thing, I see that I'm going to have Newton, the meter is going to cancel out, right? So that's nice that goes, this goes. And then the second comes upstairs, and I get Coulomb squared, but that is the junk. You see, that's what I want to get rid of, so let's divide by that. So that means the magnetic field density here, you would take the B squared and you would divide by the mu naught. And that's what you get, see? We did it in dimensional analysis to show you where everything comes from. So then, if you use the connecting equation that E naught over B naught is equal to C, then you could write B naught, and we'll put a little naught there since that's the electric field and magnetic field terminology. We're using that naught there for the amplitudes. So this B naught is E naught divided by C. So that means this is 1/2 E naught squared, or from mu naught, and there's a C squared down in there. But C is 1 over the square root of mu naught epsilon naught. So that means this is 1/2 E naught squared. Down in here I have a mu naught and a 1 over mu naught epsilon naught. These will cancel. The epsilon naught pops upstairs, and guess what? It's the same. That's the same as we got for the electric field density, the energy for the electric field. So that means the total, which would be 1/2 epsilon naught E naught squared plus 1/2 B squared over mu naught. This is the electric, this is the magnetic, and these two are equal. So you can then write this as doubling each one. We can double this one up, or we can double the other one up. Okay, nice review. All right, then we go on to the energy. This is the energy density, but we really want to know what the intensity would be. And while this here is joules per cubic meter, what would be really nice to have is the transport, in other words, the joules. Think of joules per second, that's your watts, per area. So this is the intensity. Like how much energy is being deposited or transferred per square meter? Well, to get this, the speed of light comes to the rescue, because actually we're traveling at the speed of light, so that would be perfect for us. And if you take then U times C, the dimensions there would be joules per cubic meter times meters per second, and that will get you precisely what you want, which is your intensity. This would be considered then in metric systems as watts, and this is watts per square meter. You know, W means unit, watts, not to be confused with work. All right, so that means it would make sense. Watch this trick. The U is equal to epsilon naught E naught squared. And I'm going to write this out as 2 factors of E naught. And since the connecting equation here, E naught is BC, I could write this as E naught, epsilon naught, and then E naught, and then I'm going to put here B naught C. Because see, I have these two together, and I know that if I take E cross B, I'm going to get something traveling in the direction of the light, and this is getting me close to the intensity right here. See, so what I would need here is I would need to take UC to get what I'm interested in, which would be here epsilon naught C squared. And remember, C squared is 1 over epsilon naught mu naught. So the mu naughts cancel, and I get this. Now this is also done in the introductory physics class, so really half of this class is review. All right, and this is what we get. So now it makes sense to define a vector S, which is E cross B divided by mu naught, and that's named after a physicist, Poynting, Poynting. And when I first learned about this, the teacher kept saying Poynting vector, and I kept thinking, well, this does point in the direction of the wave, so I thought the teacher meant this Poynting. But then I later found out that the teacher meant it was a scientist. His name happened to be Poynting. Actually, we have gone into part 2 of our class. So let's just put here O2. This is irradiance. This is all related to the irradiance. So when you have the irradiance, technically what you want to do is you want to average over a full period. So when you do this cross product here, you're going to get the 1 over mu naught. You're going to get the magnetic and electric fields product, but you're going to get sine squared because each one had the sign. So you're going to have this. And if you want to put the vector on there, you can. That would be then the k hat vector. So if we want to do an average of this thing, because the thing's fluctuating, since a meter is a device, an instrument's going to measure, it's going to be in real time. Remember, this omega has a frequency for visible light, 10 to the 15 hertz, that's quadrillion per second. So we really want the average of this sine over time. And that will then give us the irradiance. So that's where we're heading, that's the irradiance. So how do we take the average? Well, you take the average by integrating this over a period. We can go ahead and set z equal to 0, so we are stationary at some point, and as the wave is going to go by, will oscillate at that point. So we're looking at here, and since we're squaring the sign, we don't lose anything if we just throw that minus sign away since it's squared. And you want to integrate this over the one period, one cycle, and then divide by that time, and that gives you your average. And sometimes you'll see this written as a little bracket thing for average. Here, the average. Now, most books will pull out some half-angle formula to do this. Watch the trick that I'm going to show you. Okay, so let's go over here. 1 over t, 0 to t, sine squared. Now, the first step is going to be, let this be a theta, so we can have a nice integral to do, and change the variables. So in other words, omega t equals theta, then dt is d theta over omega, and that'll go in here. And then when the t slips from 0 to capital T, then the theta, if you look at the theta, it'll go from 0 to omega capital T, because that's what theta is, omega t. But see, omega is 2 pi f, and if you multiply, t times f, t is 1 over f, f is 1 over t, then this is simply going to get you here 2 pi. So that's nice. And that makes sense. That's one cycle, 2 pi, a sine wave. And then here, if you, at this point, just write down 1 over t for now, so we don't change too much at one time. And this is sine squared theta. Then dt is d theta over omega, and t omega is going to be the 2 pi. We already have done that, so that means this is 0 to 2 pi, and you're going to divide by 2 pi, and that's nice and clean. Sine squared theta d theta. Now, when I check books, they whip out some half-angle formula, but I was taught a trick by my undergraduate teacher and advisor, Dr. Houston, many years ago, that if you're integrating over a cycle, that this is going to be the same as cosine or sine. So we can take 1/2 sine squared plus cosine squared. So what he's basically saying there, if you take the sine wave and you square it, then you're going to get something like this. But if you take the cosine, that does, like, say that, and if you square it, then you're going to get, this is going to come upstairs like this. And what he's saying is that if you take this half and this half, you're going to get 2 wholes. So in other words, over a whole period, doesn't matter if you integrate the sine squared or cosine squared. So if you take 1/2 of that, this is 1, say 1/2, this is going to be very easy. This is going to be 1/2 integrate 2 pi. You get this is going to be pi. But if you recall, there is the 1 over 2 pi hanging around from way out in front. So that means this whole thing is going to be 1/2. All right, when you apply the 1 over 2 pi to this pi, you'll get 1/2. So 1/2. So we have the irradiance. The irradiance then would be equal to E naught B naught over 2 U naught. That's it. So now we come to a topic we're already familiar with, and that's total internal reflection. And here, we've seen total internal reflection here with the water experiment. And if we go to our equations, Fresnel equations, we have this one from the previous chapter. For the parallel case, and then for homework, you're working on this one. And we want to go from, let's see, in this case, you want to go from glass. You want to go from glass to air, all right, or water to air, doesn't matter, it doesn't matter. So N can stand for water or glass. So then, for the parallel case, you get cosine theta, N2 is 1, and this is an N, cosine theta 2. And then here we're going to have N, cosine theta 2. Remember, N1 is the N. And then this is plus cosine theta 1. And then over here, we're going to have N cosine theta 1 minus cosine theta 2 over N cosine theta 1 plus cosine theta 2. Now, Snell's law says N times sine theta 1 will be then equal to N in the air, which is 1, times sine of theta 2. And here, if we want everything in terms of theta 1, we got to get rid of this cosine theta 2. So that means here, the cosine of theta 2 would be 1 minus the sine squared, take the square root. So that's going to get you 1 minus n squared sine squared theta 1. Now, the problem here that you can see immediately is that when the cosine of theta 2 goes imaginary, in other words, when the inside of this square root goes negative, and this can go negative because that n is greater than 1, and that can then conspire to get you a negative. So when this goes negative, we're in trouble, and the square root then is going to go imaginary. So let's look at this angle, and that is a critical situation here. So this is called a critical angle when this condition is met. And I really like this because we're really getting this from first principles, this total internal reflection thing, which you learned earlier about. This is basically saying sine squared here is 1 over n squared, all right? Because we bring this on the other side and then divide by n squared, we get this result. So that means the sine of the critical angle is 1 over n. And if we then solve for the critical angle, we want the arc sine of 1 over n. And for water and glass, if you plug in some numbers, you'll get, let's see, for glass, you'll get 42 degrees for glass, and for water, you will get 49 degrees. You know, but just by putting in the 1.5 and, or you put in the 1.33. That's nice, the critical angle shows up. So now what happens though if we're bigger than a critical angle? Well, if you're bigger than a critical angle, then this thing goes imaginary. So I can write this as, I could put an I out in front and flip the order. So if I have n squared sine squared theta 1 minus 1. So now this is positive. I pulled out the square root of minus 1. All right. And then this will also go in down here. Now that is crazy. So that means what I have for RP, I have some real number minus here I times another real number, and I'm dividing by here. This would be, in this case, I have the same cosine, so that's the A, and then over here I have the same thing with the plus sign. And if I square this thing, yikes, I get imaginary stuff floating around. What is going on? Well, we don't want to square that. Remember that when we talked about phasors, that if you wanted to have the complex numbers in general, if you wanted to have the square of a complex number, you're basically doing this. in terms of physics, because you want the like the energy, or you want the the amplitude squared. If it's complex, you do this. So if we look at that as our guide and do that, then we're going to be looking at, let's say, a z. I'm just going to write this complex number z is this complex number like this over a plus, or you can just leave it. You can leave it as r, p, it doesn't matter. But the thing is, in general, anything of this form, complex number, when you do that, you write down the z, and then you're going to flip the signs on the imaginary. And when you flip the signs on the imaginary, and then all this cancels, you get 1. Now, this is incredible what this is, because this is saying that for the angles that are greater than a critical angle, which we know from our introductory, physics concepts, that if your angle here is greater than a critical angle, you get total internal reflection. Remember the 3 cases, that if you had something like this, you bend away from the normal because you're going from here, glass to air. And then if you're at the critical angle here, you skim the surface, you always get reflection. And then when you're greater than a critical angle, you can't bend away anymore and go through, so it's total internal reflection. And this is saying that the reflection for this one case, the polarization case P, is 1. You get 1. It's like, and then the transmission would be 1 minus R is 0. Very elegant. That just blows me away. It's like I would expect to have, R equal to 1 for like one value, but it's saying R is always 1. If you get beyond that, it is so elegant, amazing. And you can, you find the same result if you go up to this case, the same result, because you have something here, and then here is going to be your imaginary. 1 is going to be in there, and that is also down in here. So you have, A minus BI and A plus BI, same thing, got the same thing. So you get the 1 again. And now we go to another topic, and that's Brewster. We go here to the Brewster. I believe they'll treat this in the introductory physics. They just won't do these things, these Fresnel equations. That's advanced. That's what we're doing in this class. But they'll talk about these concepts in a simpler way. So here is Brewster's angle, or the Brewster angle. We'll go with Brewster's angle, and this is another surprise. So this is a surprise here, and this is going to be another surprise. And this surprise is that if we're looking at, say, here, I want to go from air to glass. So in that case, if I adapt this formula, the RP formula, I'm going to have here, N2 is now the glass, so I have then N cosine 1, and then minus, this is going to be cosine theta 2, and then this is going to be cosine theta 2 plus N cosine theta 1. This one is going to be, this is going to be the air. So I'm going to have cosine theta 1, that's the air, minus N cosine theta 2. And this is going to be the air, cosine theta 1, plus N cosine theta 2. Now here, N is greater than 1. If N is greater than 1, you're going to have the case that the transmitted angle is going to be, as you bend toward the normal, is going to be less than the incident one. So this means that the sine of theta 2, let's go ahead and draw a little picture here. So if you're coming in here from air and you're going to glass like this, and you get some reflection. This is the air and this is the glass, and this is theta 1 and this is theta 2. The sine of theta 2 see, will be less than the sine of theta 1, because that's the opposite. If you just make it yourself a nice little triangle there, where this is length, unit length, you'll see the sine of theta 2 is going to be less than the sine of theta 1, all right? But that means the cosine is going to do the opposite. The cosine of theta 2 will be greater than the cosine of theta 1. Because cosines and sines, complementary. When sine gets bigger, cosine gets smaller. All right, it's kind of cool to see that relationship there. So this is your cosine, and this is your sine. So if this angle, starts to get smaller and smaller, then a cosine grows, sine decreases, and vice versa. But now we get something very interesting happen. If the cosine of 2 is greater than the cosine of 1, and then the n is greater than 1, this will always dominate, and you can never have these being equal. But over here, since the cosine of theta 2 is greater than a cosine of 1, that this one's going to be less, and that's going to then knock this is greater than 1, but it's going to knock it down. It's possible to get these two to be equal, to get 0. Well, you won't get that here because the cosine of theta 2 is greater than this. So that means this is always going to win, and even the n is going to help it win even more. In other words, n times that's going to be greater than 1. But over here, the cosine of this is smaller, but when you hit it with the n, you can then make it bigger and make that work. So let's go ahead and check that out. So n cosine theta 1 is cosine theta 2. Now we know from the graph, this picture from the other class, that if we're looking at RP, that there is a place where you can zap it. In other words, at this angle, which looks like about 56 degrees with the glass. And here, when you did this one for homework, see, that's not 0. So you're not going to get 0 for that polarization. But for this one, you can get 0. So this means, if we look at this and use Snell's law, n times the sine of theta 2 is sine of theta 1, since we're going from air to glass. I wrote the glass one first there. Then if you look at these, you can find, let's go ahead and write this one again the other way. Sine of theta 1 is n sine of theta 2. So what I'm going to do here, actually, I think I like this form better, because this is suggesting if I divide this equation into that equation, left and right sides, the ends go away. I like that. So cosine theta 1. Remember, when you're deriving things on your own, sometimes you have to go a little bit in the circle to decide, but I believe that's going to be much better for us to take this approach rather than copy from a book. All right, so cosine theta 1 over the sine of theta 2 is the cosine of theta 2 over the sine of theta 1. Oh, this is nice. Cosine theta 1, sine theta 1, what a cute relationship. Cosine theta 2, sine theta 2. That's quite nice. Quite nice. Well, you might remember this from introductory physics. I remember when they had the range of a football, there was something like you got this sine of 2 theta, and the max was when theta was a 45-degree angle. Remember that? Well, if not, it doesn't matter. This can be very easily checked out. Your Euler formulas, by the way, are golden. You want to remember those. This is I theta. Always remember your Euler formulas. You might forget trig identities, but never forget Euler. So this is the sines and cosines using Euler. And then if you look at this, you get 1 over 4i. And this is a difference, say sum and difference. So that means this has to be this first one squared and minus the second one squared. Just like if you have a plus b and a minus b, you get a squared minus b squared. So this is 2i times the sine of 2 theta. And then you get the result. I mean, this is going to be 1/2 sine of 2 theta. I mean, look, by the time you look it up, we can do it. All right, so that means that the sine of 2 theta 1 is equal to the sine of 2 theta 2, just applying the identity in both cases. Now, you would, at first inspection, say, well, I want theta 1 equals theta 2. But remember here, you can't have that because the refraction of these angles are not the same. See, but wait a minute, this would also work, you know, if I'm looking at the sine, okay, so if I'm looking at the sine of this angle here, the sine of the supplement, so if I have this as alpha, the sine of, you know, pi minus alpha, that angle here, this big angle, has the same sign. So that means I could say that 2 theta 1, if these are supplementary, then I could say that this is pi minus 2 theta 2, or vice versa, all right? Like if you have 30 degrees, then you have 150. Or you have 150, you have 30. So if this is the case, this is a very nice relationship because it's saying that these angles are complementary. So, you know, we're saying here that if 2 theta 1 plus 2 theta 2 is pi, then pi over 2 is theta 1 plus theta 2, but these are complementary angles. Okay, so what we can do now is we can use Snell's law. Sine of theta 1 is equal to n sine of theta 2, and we know how the 1 and 2 angles are related. They're complementary. So that means you can write this one. I mean, if you want to show all the steps, this would be sine of pi over 2 minus theta 1, or just go ahead and put the cosine of theta 1 down in there, and the n is hanging around. So if the sine of theta 1 is n times the cosine of theta 1, then the tangent of theta 1 equals n, and that's the condition for the Brewster angle. And if you do that, you get the arc, you want the arctangent, we'll call that Brewster now. You want the arctangent of 1 over n. And if you plug in for your glass, you will get, for glass, 56 degrees. And if you do it for water, you get 53 degrees, all right? And here is Brewster. There is Brewster right there. The famous Brewster angle. Now, when I discuss this in my general student class, here's how I do it. I say you have a wave coming in with 2 polarization states. So here's electric field vibrating this way or in and out of the page. As long as it's transverse, you're good. There are the 2 cases. And then when you hit the glass and go in like this, there's a place where when you refract, that you can't have these going to the eye because that would be longitudinal. So they get killed. So you just get polarized state. You just get the one polarization. And this polarization state here that we're looking at that's going to get killed is the parallel one. The S one, which is the one that you did, worked on for homework, that one survives. So this way you can explain it to a general layperson almost here without math, all right? And that's the polarization. I got the lines, this one, and here's the dot, my fist, all right? So I'm coming down like this, and I reflect. This can't go to you because that would be longitudinal. It has to be just the fist. So just the fist, all right? So this light is polarized. Now, if you want to add a little physics on this, so that you can teach, say, the freshmen, you would say, all right, so this is the theta, this is Brewster. This is Brewster because his reflections angle will be the same. And then this down in here is your transmitted angle, so that's theta 2. And Brewster plus 90. Now, this would be for physics majors now, or introductory physics class, or even the pre-med students probably can handle this because this is just trig. We're not using calculus, and that would equal pi. So if that's the case, now you're getting the result that if you look at the Brewster angle plus the other angle, you're going to get here. Now, I probably shouldn't mix this up. This is 180. So then you subtract the 90, you get this. So you get this complementary between the two, and then you could then use Snell's law here, just like we did before. Snell's law, this is n sine of theta 2, and since they're complementary, you're led to the same conclusion. So you don't pull out the big, heavy heavy physics here with the Fresnel equations. You can work out this the easier way. Now Brewster Brewster invents, he invents a kaleidoscope, but basically a kaleidoscope had already been invented before, the idea. But he invents one, a really marvelous one, the Brewster and the kaleidoscope. And beautiful idea here. He has two mirrors, and you put some materials there, and you get reflection, you get multiple reflections. And I could imagine Brewster giving these to his niece or something, say, here's a present in a kaleidoscope, wow. And he patents it, but the word got out that the word got out about his idea, and they started making them before the patent was official, so he didn't make much money, hardly at all, when hundreds of thousands of these things were sold. Here's a nice analysis with 90 degrees. If you have 90 degrees, this is not your typical kaleidoscope, but the principle will be evident. This, you make a pizza pie, four big slices. This reflects underneath, and then when you hit this mirror, you'll reflect over here, and you then have a degree case, and you have one object, 3 images, you have 4 things, and if you use the formula 360 divided by 90, you get 4. Now, if we look at the case where there is a 60-degree angle, and then we go pizza pie, we got 1, 2, 3, like this. This is a symmetry here. You want all the angles to be 60. 1, 2, 3, 4, 5, 6. So this one here, 1, 2, 3, 4, 5, 6. So here, this object would have an image upside down. Then on this mirror, you would have here. And then when you go back to reflect again, remember this object, if you had this mirror standing straight up and you leaned into the mirror, your image would lean into the mirror. So just take this and turn it sideways, and you get this. And then, so this is here, bing, bing. It's got to be 120, 60, 60. And then if I want this reflecting back here, I go bing, 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 bing. So it has to be here. And then you're finished. And once again, 360 divided by 60 is equal to 6. I didn't draw this the best way. 60 would be a little bit bigger, like this. And then if you did your pizza pies, you got your slices. Now they look similar. So this is a little better diagram than that one. That was more like a 45 degree or something. So here you got that, you got this, and you got that, and this. This looks more accurate. All right. Okay, so n things is 360 divided by the angle when there's a symmetry and they overlap, because the multiple reflections, they'll wind up overlapping where they are, and you're finished. So we then go to 06, the polarizer, and Edwin Land, the inventor. And here, polarization, you can demonstrate with a string very easily. This is what I do for my students in the non-math class, in general class. This is your vertical polarization, shaking a string, or this would be like an electric field. And then here you could shake this way, it's horizontal polarization. And Edwin Land, he developed the Polaroid. This is the turn of the century. They knew about polarization, goes back far. We'll see in a second. We'll go back to the 1600s and talk about calcite. But here he invented this polarizer, this sheet, and he's a freshman at Harvard. And here, these 3 great inventors and developers. You got Jobs And Jobs, by the way, looked up to Land. Land was his hero. And you have Gates, Bill Gates, Microsoft. And all three dropped out of college. So I'm not suggesting you drop out of college, but the three of them did drop out. And here, a 17-year-old freshman invented a sheet where the light comes in with mixed polarization. If you orient this a certain way, like only one passes through. Then if you crisscross them, this won't let this one through. So this one is letting through the horizontal one, and it absorbs the vertical. Now, if you then turn it so that this one will only want the vertical, then since this is not vertical, you get nothing. And here, we're doing the same thing with orient this vertically, so the vertical one goes through. But then if you turn it like this, then you kill it. So, if you had lined it both the same, well, then they go, that same one goes through. So this is related to the Brewster angle because when you get a reflection off glass here near the Brewster angle, you get yourself a polarized light. So I put a polarizer on my camera and I turned it, and look, I killed that reflection. Also mysterious fluor. We thought that was poison, but it looks like it was some kind of light interaction with the vinyl from the 80s. When they stopped making that kind of vinyl. Not good. So here's another one. I'm down in my den, and this light hits this glass, and it's near the Brewster angle. It's going to be polarized. So if I take a polarizing filter and turn it just right, I can kill it. See, I can kill it. Isn't that nice? So that is cool. Here's another example. Actually, I was on the tenure committee with Tracy Brown, and he's reading student evaluations. I had read mine earlier. And, UNCA really values student input. So we're on the tenure committee, and we're looking through pages and pages of student evaluation. So I'm going back fooling around, maybe trying to bother him or something there. And I can see his cool head there reflected in the glass. So I put my polarizer on because I figured that's kind of close to the Brewster angle, around 56 degrees, around 60 degrees. And then I was able to knock the head out. So if you are working for a newspaper, you might want to put that polarizer on there and kill that reflection. But I thought the head was cute. I liked them both. I liked them both. And then here at my home with the piano, notice that even the reflection off the piano, you get some polarization. This is not glass, but it's like a shiny finish. And if I put the polarizer, I turn it, all these are taken with polarizers. So you can see the effect of having a polarizer on the camera. Okay, then just a quick inspiration here. If we look at Edwin Land, his daughter, 4-year-old daughter says, Daddy, why can't I see the picture right away? And he's thinking, wait, I can do that. He walks quietly. And this is always good to walk quietly, think, walk in the woods. He walked at Santa Fe. He walked for several hours. And he, in his mind, got the general idea of developing the film in the camera. And it took him about 4 years to do it. But Daddy, why can't I see the picture now? That question, that's amazing. So you invent the Polaroid camera, which developed, because in those days you had to take the film and send it to Kodak and wait a few days to get it back. And Jennifer said, why can't I see it now? And he invents it. And then took him to 1963 to get the color, and then in 1972 he had it so that it would develop right in broad daylight and you wouldn't have any refuse to throw away, no chemicals. And then we got digital cameras now, so we don't use this. But this inventor, when he was asked about invention, I like it when these inventors talk. Edison said invention was 1% inspiration and 99% perspiration. And here you can see with Land, in 3 hours, he gets inspired to invent the Polaroid, it was going to call it the Polaroid camera, an instant camera. It takes him 3 years to actually develop it, 3 or 4 years. And he says here about invention, you always start with a fantasy. Part of the fantasy technique is to visualize something as perfect. Then with the experiments, you work back from the fantasy to reality, hacking away at the components. I love that philosophy. Derive everything is one of my philosophies, and this is my philosophy also. Imagine something perfect. Say I want to be a pianist. I imagine the perfect performance, and then I hack away at the details and practice like crazy for months and months and years to reach that goal. So just imagine whatever you want to be in life, imagine being that, and then you work backwards and hack away at the details, like, for example, doing a homework problem in an optics course, which is part of a sequence of a physics major, which is part of a degree. And it's just neat to be inspired by these inventors. We now move on to another review. Malice's law that deals with polarizers was covered in the introductory physics class. I'm assuming that you were sick that day. And here we have the electric field, say, along the x-axis. And really don't care about the magnetic field, because the polarizer is going to work on the electric field. And say the polarizer is oriented at some cosine theta I hat plus sine theta j hat. In other words, this is polarized like vertically coming your way, but then you can have the polarizer like at some angle, theta. And if it's lined up, 100% goes through. And if it's crisscross, you zap it. You're going to get like 0. So if you want to know the part that's going to get through, is the component. You can think of this as like the two components, the one that's projected along the n-axis, which is going to be ex, cosine of theta. So another way to do it is just to have the polarizer vertical and then have some slanted E, coming in, so that there's some angle theta. And here you can think of this as like an X and a Y. There's like an EX and an EY. So I kind of like to do it this way, where I have an EX and EY. And also, well, it doesn't really matter, because you're going to take that projection, you're going to get this, and then when you get the intensity, you're going to square. So that's going to be some I max cosine squared theta. And that is Malice's law, which was talked about, in that introductory physics class. Notice how we avoided the Poynting vector and we just used a dot product. And here, if that electric field is lined up, theta is 0, you get the max, cosine 0, 1. And if theta is 90, we're checking now, then cosine 90 is 0, and that gets wiped out. 07, circular polarization, very, very easy. What you do for circular polarization is, here we're going to have an electric field that it has we're going to be at some like slant, where we have, say, an X component and we have a Y component like this, say cosine or sine, doesn't matter. And here, what we're going to do is let these be equal. And if you let those be equal, then when you look at the situation, you will get an I plus j hat, which will be some slant, and you got linear polarization, so that's linear. So what we're going to do here is look at cosine minus omega t plus j cosine minus omega t plus pi over 2. We have let the z be 0, and then let omega t be theta. So this is cosine minus theta is the same as cosine plus theta. And here, this would be the sine because of the complementary angle. And so here you have this nice result that you have I hat cosine theta plus j hat sine of theta, and that is along a circle where you have your angle, you have your cosine and your sine. And since this is omega t, this is going to just pick up and go, let's rotate. And since this right hand goes with that and points in the direction of the motion, that's called a right-handed, or say right circular polarized light. So that's right circularly polarized light. And if it were going the other way, you'd have to use your left hand. That would be left circular polarized light. So that's kind of neat that you can get that effect. And notice here, this is X and this is Y. And here Z points out of the page. Because remember, if you have your I hat, across your J hat, that gets your Z, which is going to be out of the page. So that means my thumb is pointing in the direction of the traveling wave, and it's circular polarized. And then we go to 08, birefringence. And birefringence, this is Bartholin discovering, this is back in the 1600s, where they had discovered calcite. Calcite structure is not your same, looks the same in all the directions, like some kind of simpler cubic structure or cubic structure. This calcite is such that the electric field will travel at different speeds. All right, in this particular picture, by the way, the green is your calcium, your gray is your carbon, and your oxygen is your red, and the formula is CaCO3. Nice, calcite crystal. And you get double vision because, the perpendicular and, the two different, like the parallel and the perpendicular, just imagine them as like traveling different speeds, different bending of light, different refraction, and double vision. And Bartholin called one the extraordinary ray. In other words, you have your ordinary refraction, the ordinary ray, and then you have your extraordinary ray, double vision. These are amazing. Look at this. Here's another one. All right. And now we're doing geology. This is like deep stuff in geology, birefringence in gems and in rocks. Very, very cool. So we add geology to our interdisciplinary topics. And here's another one. Look, this here in the graph paper. Now I just want to mention the last two things. Optical activity. You have optical activity in some things like Caro syrup, some sugars. So the optical activity rotates the polarization state. The molecules are such in there with these sugar molecules that you can get this effect. And if you rotate them and you rotate the colors differently, wow, you can get all kinds of cool effects. And here's one demonstration where they show you these colors. They put polarizers and you can turn it one way or the other way and get the complementary color. So this is fascinating. I just like you to know about optical activity. We're not going to analyze it though. And then also I'd like to mention here an artist, Austin Wood Camero, who uses birefringent materials. Now you have polarizers, so this is taken with a polarizer. This would all look like black and white. I mean, or clear. This would basically look clear. So Austin Wood Camero, she makes art with birefringent materials. And the birefringent materials, you need to have your polarizer there to see the colors. And if you rotate the polarizer, you get the complementary colors, you go 90 degrees. And she coined the word collage, like a collage, like you have an work of art using polarization. So she has to have polarizers on for glasses so she can see what she's doing. Otherwise, this will not have color. So here's an example from class where I have a plastic. This is coming from little bits of wrappers and things, birefringent materials. It was given to me by Chase Ambler, who taught at Asheville School for many years. And if you rotate the polarizer, look what happens. And then when you have the polarizer, you pick up the different colors because they get rotated, the different colors, the polarization gets rotated differently, and you make a color from something that has no color. Like there's no color here. Look at that, man, no color. What was that? No color. And what's really neat is that if you go 90 degrees, you get a complementary color. So yellows turn into blues. Isn't that cool? She coined that word many years ago, collage, polarization, collage. So she actually makes a cool picture, you know, like the fish or something. This is just Scotch tape and cellulose just randomly put in the slide. Okay. That's really cool. I turned it around the other way. Doesn't work, because now the polarizer, you got two polarizers together. So remember she said she has a polarizer, then she got the clear stuff, and another polarizer. Isn't that cool?